All right, so section 3.1 starts a chapter of 5 sections, but the first 4 sections all have the same flavor. And that flavor is that we're going to verify trig identities in some fashion. So let me talk first about what that means. So if we have 2 functions, f and g, then they are said to be identically equal if f of x is equal to g of x. So at every x value, the f of x or y value is equal to the same thing for both of them. Okay? So if their x's are equal, their y's are equal. Such an equation is referred to as an identity. And the goal over our next 4 sections is to be able to verify that a given equation is an identity. Now, you have seen identities before trig. You encounter them in solving systems of equations, which is usually in an Algebra 2 course for the first time, sometimes end of Algebra 1, depending on curriculums. And what happens is that there's some point along the way when you're solving a system of equations and you end up with something that says like 3x plus 2 equals 3x plus 2, and you're like, now, hey, wait a minute. If I go subtracting anything else, it's just going to zero everything out. Do you ever remember that? Does that sound a little bit familiar? Okay, you've seen it before when the left-hand side looks exactly like the right-hand side at some point. And what that means is that any x value will work. And so you wrote something down probably like infinitely many solutions or something like that, okay? That's called an identity. It just means that the left-hand side is exactly the same as the right-hand side. And we change things with identities all the time. For example, if you wrote, this is a very unexciting one, but if you wrote 4 is equal to 8 over 2, that's an identity. They're just exactly the same on both sides, right? Just different expressions for them. And this is actually a really good description of what we're doing. We're going to have things that look different on the left and the right, but they're really just different ways of writing the same thing. But we have to figure out, well, it's not really true. They're going to tell you that there's a way to figure out that the left-hand side and the right-hand side actually really are the same. All right, so these first 4 sets of identities on here are the first 4 that are on the other sheet that I gave you. So you can fill them in if you need to write them down. If you've printed things off, they're already printed off. I gave you another sheet that they're already on there, so feel free to just read these with me. We have our quotient identities, which we've seen before. So tangent is sine over cosine, and cotangent is cosine over sine. Okay? We have our reciprocal identities. The cotangent is 1 over tangent. The secant is 1 over cosine, and the cosecant is 1 over sine. We've seen all these before, right? We've used them when we've established our unit circle, when we've talked about specific values. The Pythagorean identities, we've talked about these too, but we haven't used them nearly as much. The one that people tend to remember the easiest is that sine squared plus cosine squared equals 1. I have a very distinct memory before trig when I was in high school of taking an ACT and doing like an ACT prep course and them saying, the most important thing you can remember about trig, since you haven't taken it yet at all, right? Because they're going to ask you something on the ACT, is that if you see sine squared plus cosine squared, you need to know that's equal to 1. It's a random memory. I don't know why I remember that, but it's important, and it's something that does show up. The other 2 don't show up as frequently, but they're also still Pythagorean identities. The tangent squared plus 1 is equal to secant squared, and the cotangent squared plus 1 is equal to the cosecant squared. Okay, they don't have exactly the same format as sine squared plus cosine squared equals 1, right? The 1 and the other trig function are kind of switched locations. So some people trip those up because they remember them in the wrong order. The order matters. The tangent and the cotangent is what's grouped with 1. The secant or the cosecant is what's not grouped with 1. Also, the co-function here goes with the co-function here. Those are ways that can help you to remember that they go together. And then the other 2, tangent and secant, would sort of by default go together. We've seen the even odd identities before. I'm not asking that you memorize those at this point now. We've talked about them in the sense that you did need to have them learned anyway for a test that you had done before. But the sine and the cosecant and the tangent and the cotangent, these 4, they're enlisted in a different order on your paper because my screen doesn't support going as wide unless I make the font too small. Those 4 are called odd identities. So if there's a negative angle on the inside, it moves to the outside, becomes a negative on the outside. Those are the odd identities. And then the 2 here in the middle, cosine and secant, are actually called even, and they have to do with the fact that if you were to graph one way to think about it anyway is that if you were to graph them, it's the mirror image, like symmetry around the y-axis. So the negative angle doesn't affect the value at all. And so there's just nothing there. So this is really important. Establishing identities. This is not the same thing as solving an equation. You have seen things to solve equations for years now. And when we see equals, we usually think, I'm supposed to solve something. It's not what we're doing here. We are not solving equations. So there are some techniques that you use in solving equations that you can't use because we're not solving equations, like adding something to both sides, multiplying something by both sides, moving something from one side to the other. You can't do any of that. And there's a good reason for that. The only reason that you're allowed when you're solving equations to move things around like that is because you know it's equal to start. And there are properties of equality that says, okay, if these two things are equal, right, if these two things are equal and I add a little bit here so it makes it a little heavier, I have to add the same thing here, right? That's a property of equality, and it works for addition, it works for subtraction, multiplication, division, taking square roots, and a number of other things that we do when we solve equations. But we don't know that these are equal to start with. We're trying to show that they are, okay? So we can't do things that manipulate both sides of the equation. What that means is that we're actually going to be able to be only working with one side at a time. That's what's going to happen. All right, when we verify an identity, we're trying to prove that they're equal. We cannot assume that they're equal. I think I said everything pretty much on that slide, okay? So there are some strategies. This is not like a list of like step 1, step 2, step 3. It's not that kind of a list. But these are some strategies that we can use when we're attempting to prove an identity or verify an identity or establish an identity. Different resources call it different things. The first thing you need to know is you need to know those fundamental identities, the ones that we already talked about. The first 4 on this paper, you need to memorize the first set of 3, right? Okay, you need to know those. A second step, something that's helpful to do, is to decide which side of the equation looks more complicated. And you're going to use that side that you're going to manipulate, and the other side you're not going to touch. You're just going to leave it right alone. Okay, so you're only going to manipulate one side or the other. Sometimes there's a guaranteed, absolutely should manipulate the left-hand side. And sometimes you're going to look at it and you're like, I don't know which one to manipulate. And so you're just going to pick one, and it's going to be fine. And if Carson picks one that's different from Jonas, it's going to be fine, and we're both going to be able to solve it, and it's not a problem, right? We're going to be able to establish it's going to be okay. When in doubt, one option is let's just turn everything into sines and cosines and see what happens. And that's not a bad way to do things, especially if you see some reciprocal stuff showing up and some tangents and some cotangents showing up. Just flip it all into sines and cosines and see what happens. Factoring. Factoring does not show up all the time, but when it shows up, it's very useful. Okay, so we'll see an example of some factoring ones today so you can see what that means. Number 5, keep the goal in mind. Okay, so what this is really like is it's like you have one question. Let's say the left-hand side is the question and the right-hand side is the answer. And you don't know it's the answer because they told you, but you can even think about what you do when you're working in a traditional math textbook and you know that the back of the book has the answer. And your goal is to try and figure out how to get to that answer, right? That's our goal here too. We're going to take one side of the equation and our goal is to figure out how to turn it into something on the other side. There may be lots of things that can be changed into. In fact, there are. But we need to remember what our goal is. Where are we headed and how are we going to change things to get there instead of somewhere else? And then the difference of squares is a factoring identity that you need to remember, and it often shows up in a way that we don't always recognize. And so I want to mention it very specifically. Difference of squares, when you see it in algebra, looks like this. Okay, that looks familiar, right? Okay. This is an application of difference of squares with trig. And it's the one that we see happen pretty much like all over the place when it happens at all. So if I have one minus sign and I have one plus sign and I FOIL that out, right, if I multiply it all out, it ends up giving me 1 minus sine squared. So the reason that that's helpful is because 1 minus sine squared is a Pythagorean identity that's equal to cosine squared, because sine squared plus cosine squared is equal to 1. And it comes up enough to deserve its own sort of bullet point here, because we don't always recognize it, and we want to remember that it is sort of in our tool belt of things to try to use. Okay, we got to try some though. You ready? Okay. We have, I think, 7 of them to look at. Let's start with this one. One side definitely looks more complicated than the other, right? Which side? The left. So we will not touch the right-hand side at all. It's going to sit right there all on its lonesome. And we're going to, that's our goal. Our goal at the end is that it's going to equal cotangent of theta, okay? And so we want to manipulate cosecant and cosine so that that will happen. Any ideas of how we could change one or both of those two functions on the left and it be useful to us? Isaiah, I feel like you're looking at me saying, yeah, I know what I should do.
No, but you can turn cosecant to 1 over sine.
I think that would be great. Yeah. So Isaiah says, hey, cosecant, that has another form. And it does, right? It has the form 1 over sine. Now, it probably is good to mention this one's going to work out beautifully. That's a great solution for this one. If we try something and it doesn't work, you have an eraser, right? You just erase it, we try something else. Everybody good with that? There's going to be places where you're going to try something that's not going to work. This one does work. This, if I think about it being multiplied like that, can actually be merged together into a single fraction. This is the cosine of theta over the sine of theta. What is the cosine of theta over the sine of theta?
Cotangent.
It is cotangent. And what we used are 2 identities here. Just a second. We used a reciprocal identity at the beginning, right? This piece right here was a reciprocal identity. And this, when we got to here, was a quotient identity. Do you have a question?
Yeah, so what other steps could you have taken?
There's not always a lot of other steps to take. You could actually start with the other side of the equation. That would be an option.
Okay.
I mean, that would be the only other option really here to deal with, yeah. At this point, we see that we ended up where we wanted to end up and we're done. Okay? So I'm going to write this sort of like drawing an arrow up and bending, I'm going to check mark every time I do it. But another way that I have done it before too is to indicate at the end now I'm where I need to be. Right? The left-hand side really does equal the right-hand side. And I didn't touch the right-hand side to make that happen, right? Right. Okay, don't touch the right hand. Well, don't touch one side. This time it was the right-hand side. All right. Which side would you like to start with?
Right.
Probably the left. Probably the left-hand side. It's kind of a mess, isn't it? Yeah, it's kind of a mess. But there's some mess there that's actually not too bad. Does anyone see an identity that you could use pretty readily on the left-hand side? We don't have a secant squared, but I think what you're saying is that the top is equal to secant squared. Does that sound right?
Oh, yeah.
Yeah, cool. Just make sure I understand. So Braden noticed that this piece up here at the top is one of my trig identities. It's a Pythagorean one, right? Tangent squared plus 1 is equal to secant squared. So I can replace the top with the secant squared. This one says alpha, so we'll make sure we're writing alpha, divided by the secant of alpha. It's a Pythagorean identity. Do you see it, Asia, on your paper? Nope, it's on the front page. Pythagorean identity. We're only using identities through even odd today. Okay, so from 1 down to 4 on that front page that I gave you. Okay, Pythagorean identity. Tangent squared plus 1 is secant squared. Okay, you're going to memorize it by Monday. So yeah, that's one of them. That's actually really nice. What is secant squared of alpha divided by secant?
Secant.
It's just secant, right? This is like having x squared over x squared. They cancel. If it helps you to see it, you're welcome to write out what secant of alpha squared means. It means I've got secant of alpha times the secant of alpha. Don't have to write this, but I just want you to see that's what's happening, right? We're able to cancel one of them. So whether you write that step or whether you jump straight from here to here, this gives me secant of alpha. And we're done. That's what we were going for, right? That's what the right-hand side said. This piece is now equal to this piece, and we're finished. Okay, how are we doing? Okay, so far? All right, let's keep going. They looked pretty okay until number 3, right? There's a lot going on number 3. And even looking at this, I think that we could probably do the left-hand side or the right-hand side and call it the more complicated side, or at least say that they both look complicated, correct? You want to do the right? Okay, we're going to do the right because Isaiah suggested that we're going to do the right, which means it's not going to match my notes. So we're just going to see how it goes.
Good.
You ready to go? Okay, we're going to give it a go. All right. The thing that's interesting that's happening here is that there's factoring. This is actually why I put this example on here. There's factoring that goes on. So whether you're working with the left-hand side or the right-hand side, pick one. What you should see is that you've got 4 of one function, right? It's a power of 4, and then you've got a power of 2. Does everybody see that? Okay, so we're going to work with the right-hand side because Isaiah's running the show today. It's okay. It's all good. They both have tangent squared in them, right? One of them is tangent to the power 4, the other is tangent to the power 2. So they both have 2 tangents, right? Tangent and tangent there. And so I can factor a tangent squared out. Well, if I factor a tangent squared out, there's still 2 tangents in the first piece. Because there were 4 there, I pulled 2 out, I still have 2 left. When I pull the tangent squared out of tangent squared, what am I left with? I'm left with a +1. Don't forget the +1. Sometimes people forget and think that they've just eliminated it somehow completely. It's not 0, it's 1. Factoring is division that you can still see. Okay, so we pulled it out. And what is tangent squared +1? That is secant squared. We saw that just a moment ago, didn't we? This piece right here is secant squared. Now, that's movement in the right direction because what's the left-hand side using? Secants. So I still have a tangent, though, on the right-hand side that I need to manipulate and so sort of somehow eliminate. So how, and notice everything on the other side's at secants, right? So again, the goal, what's the goal? Because there's things I can change tangent into. I can change it into sines and cosines. I can change it into secants. What's the goal? The goal is secants. So how could I manipulate tangent squared so that it involves secant, not sines and cosines? That Pythagorean identity again. Now, let me write down what the Pythagorean identity says down here just as a reference point for everyone. It says the tangent squared +1 is secant squared, right? That's what the Pythagorean identity says. But if I am trying to take tangent squared and to rewrite it, what will it be replaced with? Secant squared minus 1. You're exactly right, Anna. This -1 has to move over here, right? So if I wanted to do this replacement, which I do, I'd have to shift the 1 over to make that happen. So up here, this tangent squared is going to be replaced with secant squared of x minus 1. I know we've talked about this before, but I'm going to remind you again. The variable, whether it's alpha or theta or x that I'm putting inside of each of these trig functions needs to be there. These functions have no meaning apart from the variable angle input inside of them. They don't mean anything. It's like you telling me square root. Well, square root of what? If I don't have something inside the square root, it doesn't mean anything. So make sure when you're writing these that the angle, whatever the letter is, variable is they're using is still there. Secant squared minus 1 times secant squared. Now what? Distribute, exactly. So we're going to distribute this out. This is going to be secant squared of x, secant to the 4th of x. So we're distributing like this. Minus secant squared of x. And it's equal. We're done. And we totally dodged a bullet because my notes used the other one. Right? Okay. That's kind of the point, is that it doesn't matter which side you use. Sometimes there is a natural choice. And sometimes it's just like either or is just fine. It doesn't really matter. And this is a really good example of either or doesn't matter kind of thing. Okay? Any questions on this one? All right. I think there's a harder side on this one, though. I think we're going to work with the left-hand side here. Any ideas of what you might want to try? Carson?
Just add the 2 signs together.
You can't add the signs together because they're each multiplied by something that's different. However, you can do something with the signs.
I mean, you can convert your secant, cosecant, right? I don't see any other steps.
We're going to deal with the cosecant and the secant in a second. What do you have in mind? Anna, did you say something? Factor it out. So you noticed there's a sine squared in both of them, right? We see them. Everything on the left has a sine squared in it. I can't combine them because they have other pieces that are multiplied by them. But what I can do is I can pull it out in front, kind of like the last problem that we did when we said, hey, everything's got a tangent in it. Let's pull a tangent out. Oh, I can actually pull out tangent squared. I can do the same thing here. So I can pull out a sine squared. Alpha is being used here, so we'll use alpha again. And then I've got secant squared of alpha plus cosecant squared of alpha. All right. Now what? Ouch. I know where my, oh, right there.
You convert your secant, cosecant to 1 over thing.
Okay, so we could. We can use identities that will change the secant and the cosecant into like the reciprocals, or even to their quotients. If they had quotients, we could use quotients here. We don't have any quotients. I don't know why I said that. But yeah, I think that's as good a place as any at this point to go from. So let's give that a try and see what happens. So if I change the sines or the secant squared alpha into its reciprocal, that's cosine squared of alpha. And then the cosecant squared is 1 over sine squared.
Distribute.
We could distribute. Now, at the point where we are, that's a really good step. What that really means is that maybe pulling sine squared out at the beginning wasn't as helpful as we initially thought it was. There's no way to know until you try something. Are you with me? Okay, so you try something and you see what happens, and if it doesn't work very well, it's going to undo itself, or you're going to get to a point where you're like, okay, scrap it all, let's start over at the beginning and do something different. This is fine at this point. So if I multiply this through, I'm going to get sine squared of alpha on top and cosine squared of alpha on bottom. And then over here, what happens when I multiply this one? Yeah, this cancels. Cancels to what? 1. Please be careful when we use the word cancel that we know what we're canceling to. Things are said to cancel to 1, and they're also said to cancel to 0. It's a really terrible math term that we use that way. So just be careful. Okay, well, sine squared over cosine squared. I'm not really quite where I want to be, right? But is there another way that I could write sine squared over cosine squared? I could write that as tangent squared. Yep. So let me make mention of the fact that if we had wanted to, we could have gone straight from here to the reciprocal part instead of factoring it out, and that would have worked as well. Now that we see that, that's an option. But Braden's exactly right. Tangent squared plus 1. Apparently this is our favorite theorem of the day. Everybody's going to remember this one now because we've used it. This is the 3rd time it's come up, right? Yeah. This one's secant squared. And what does that say? We're done, because that's where we were headed to begin with, right? We were headed to turning everything into secants. All right, you ready for the next one? The next one's long enough that I actually had to make the print smaller to fit it on the screen. It is the longest one on our examples that we're going to do, so it's a little bit smaller for that reason. Again, there's a very clear place to start on this one, right? You've got a mess on the left. It's something very simple looking on the right. We're going to work on the left. Cool with everybody? All right. Suggestions. What would you like to do? I'm really trying not to tell you what to do because I've got an answer written down, but I want you to understand that there's lots of ways to get there. Does that make sense to everyone? So somebody suggests something, we're going to give it a try. What do you have, Olivia Grace?
Cosecant squared, the 1 plus cotangent.
Oh, but we only have 1 plus cotangent, not 1 plus cotangent squared. Okay.
Distribute out.
So we may use something of that later, but we're not there yet. So secondary option, what do you think?
You can distribute your sine cosine.
Okay, we could distribute and see what happens. There's definitely some parentheses here, so that's a natural place to start too. Okay, so let's give that a try. Let's distribute it and see where we are. This would be sine squared of x plus sine squared of x cotangent of x. And then we can distribute the next one. So I did this, right? And now we're going to do this one. I have cosine squared of x minus cosine squared of x tangent of x. And then I've got this lonely kind of cotangent squared here on the end. There are things that we can simplify right here really nicely. Does anybody see something that simplifies really nicely? We have a cotangent and a cotangent. Okay, Braden, are you asking me to do this piece? We can't subtract those two, and the reason we can't is because this cosine is attached. It's multiplied with the tangent, okay? I really appreciate you guys mentioning things that are places that we get tripped up, because just because Braden was thinking it, there's probably 5 or 6 other people who thought the same thing. It's a really easy algebra omission that we have sometimes, so thank you for that. I appreciate it. Do you have another thought? You were agreeing with him. You were agreeing with him that you saw the same thing. Yeah, it's easy to do, right? Especially because they're right beside each other. Something else.
Could you add the sine squared of x to the sine squared of x, or is it also?
For the same reason you can't. The sine squareds at the beginning can't be added because one of them is multiplied by cotangents. Yeah.
The only thing you could do is to convert your cotangent.
We will. I really want to do something else first. I know I'm told you I wasn't going to lead the direction, but I really want to do something. Olivia Grace, do you see something?
Could you take the first sine squared x and then the cosine squared x and make it equal 1?
Yeah. I really want to do that at some point, and here's a really good point to do it because we'll have to write less. They're not beside each other, so you might not have seen them write very quickly. But those two pieces are an identity. What's sine squared of x plus cosine squared of x? It's 1, and it'll let us write a little bit less down. So I'm going to take those pieces and write them as 1. I'm going to write the other pieces out that we have, and then we're going to have to figure out ways to combine them. It may not feel like we've made a lot of progress, but we actually have made pretty good progress. We've eliminated a couple of the pieces that were there, and we've replaced them with the number 1. That's pretty friendly. Any thoughts next? Olivia Grace?
Cotangent squared and then the 1.
Let's see. Ooh, isn't that nice? There's cotangent squared, and here's a 1. What is cotangent squared plus 1?
Secant squared.
That's secant squared. So we can combine those two. Cool. So it doesn't, result in a 1 like the last one consolidated, but it does result in some consolidation. You can write it at the end or you could write it at the beginning. Doesn't matter. I'm going to write mine at the end just because I'm moving over here from left to right. Was it cosecant squared? Okay. All right, what's next? Or what other thoughts do we have? You could turn tangent into cotangent, but I don't know that it'll be very helpful. Let me show you why. If we change it into cotangent, it will look like, I was thinking this one, but either way, you just end up with a denominator and it doesn't match with the other one perfectly. But there is a manipulation that we could do, but just not quite that one. Go back to our list. It was on page 2 of the notes for today. Go back to our list, and I will on screen as well, of things we can try. We're using the fundamental identities as we go. Do you have an idea?
The cosine of 1.
Okay, so which one are you manipulating?
Cotangent.
Okay, so what I think you're seeing is what we're calling on here step number 3, expressing things in sines and cosines. Okay, so the quotient identity can be used, and it's a really helpful one here. So in essence, what we're doing is we're turning things into sines and cosines. And the reason that that's helpful is because we already have some sines and cosines that we're hoping will disappear. So the cotangent is cosine over sine. And then the tangent is sine over cosine. Please notice, every single time I rewrite it, I rewrite everything there. I don't just manipulate with one piece and ignore the rest and then drag them back in at the end. Every step is equal to the next step, right? Every step is equal. And unfortunately, with my math lab, nobody's forcing you to do that along the way in the same way that it would be if I was grading homework, right? So be careful, because your quizzes, your exams, I will expect to see every step equal to the step before. What happens with these quotient identities that have been changed now? What do you notice here? There's some canceling that can happen, right? So this sine will cancel with one of those signs, and I'll be left with sine x, cosine x. And what happens in the second set? Same thing with the cosines. One of the cosines in the cosine squared, and that denominator of cosine will cancel, leaving me with cosine x, sine x. Mm-hmm.
Like in the previous step, you can kind of see like the opposites of each other, and like they're just going to cancel out. You have to do those next two steps.
You do, because you can't see that they're opposites of each other.
Well, like the cotangent and tangent.
But they aren't just negative of each other or something like that. We can't just manipulate them that way. Sometimes they will sometimes your expectations are going to be ruined when you make these substitutions. Here they weren't because of what you thought you were seeing, which is great, but sometimes they will. What happens here?
You can just subtract those.
Those are exactly the same, right?
Yeah.
So I think it is probably worth mentioning that the order of the multiplication doesn't matter, right? Okay, that's called a commutative property. You've learned it when you were itty-bitty. You didn't call it that when you were itty-bitty. But when you were learning things like, 3 times 5 is 5 times 3, that's the commutative property. That's second to third grade. You've been doing this for a long time, and it works with functions as well. So sine times cosine is the same as cosine times sine. These two add to 0, right? This is 0. So this just leaves me with the cosecant squared of x, which is great because that's what we wanted, right? That is the answer that we were shooting for. So sometimes people really hate identities. I actually think that they're kind of nice because you know what the answer is supposed to be when you're done. There's no question. You know exactly where you're headed. And that's not true in most math situations, right? It just isn't. And this actually has that flavor to it. Okay, we have a couple more. This is another one of those cases where I really think you could manipulate the left or the right and make it work. So does anybody have a preference of which one you would like to manipulate?
The right side.
You want to do the right side this time? We usually do the left, so let's do the right side this time. Okay, if we manipulate the right-hand side, there's only one option that we have. I shouldn't say there's only, but there's one sort of reasonable option that we have when you're looking at it. If we're working on the right-hand side, what could we do? We can't get cosecant squared because we don't have 1 minus cotangent squared, or 1, and it's plus 2. So what's that? So we can manipulate the cotangent into something different. We could turn it into tangent, but considering where we're wanting to end up, that might not be the change that we want to make. Yeah, so since there's cosines and sines on the left, that's probably the one that's going to be the best option for us at this point. Okay? So keep reminding yourself as you're looking at these, where am I hoping to end up? On the other side, I have sines and cosines, so manipulating this into sines and cosines is going to be the most helpful for us to do right now. So we're going to change this into 1 over, it's 1 minus, and then it's cosine of theta over the sine of theta. Okay, does that make sense? Okay, so there's a name for something when there's fractions inside of fractions. It shows up in Algebra 2. We're hitting a lot of Algebra 2 stuff today, I guess. Shows up in Algebra 2 as well. And they're called complex fractions. They just mean there's fractions inside of fractions. And so that's the name that they're given. They're complicated or complex. We don't like fractions inside of fractions. Nobody ever let you leave an answer like that. And the manipulation of that is actually part of what's going on here that's going to help us, right? We don't want it in that form. We want it to look like what's on the left. So any thoughts as to what I can do to eliminate the fact that I've got fractions inside of fractions? Yeah, we're going to multiply by the denominator of the little fraction. So this piece right here, this sine theta, we're going to multiply by it. It's the equivalent of finding a common denominator. If you were thinking, how about a common denominator here? But it makes it work faster. I don't know about you, but faster is good. I like faster usually. And you don't lose anything in the process. Sometimes you do things faster, you lose something. I get that. But we're not going to lose anything by making this faster. Obviously, the numerator, it just becomes sine of theta. Right? I've got 1 times sine of theta, that's sine theta. But the denominator is a little bit trickier. We have to remember there are 2 pieces in this denominator. And if I'm multiplying by the sine of theta, I have to multiply both pieces by the sine of theta. So the 1 gets multiplied and the fraction gets multiplied. So if I multiply the 1 by sine of theta, that's the sine of theta. And what happens when I multiply the fraction cosine over sine by sine? Yeah, the signs cancel. That's why we want to multiply by the denominator. I mean, yes, it leads us where we want to go, and that's great news. But the reason, right, the motivation for multiplying by sine is that it's going to eliminate the little bitty fraction by eliminating the little bitty fraction's denominator. If it helps you to see this, you're welcome to write the sine of theta on both sides so that you can remember. Let me do this way. Oops. That you're going to multiply it here. And then as you multiply it here, these can cancel. So if it helps you to see those cancel, like in written form, you can do it that way. And I am left with minus the cosine of theta. And lo and behold, what happened? That's actually what the left-hand side happened to be. It's not the only way to do this problem, but it's a pretty good one. It's a really clean way to do it, and it worked really well for us. Okay, we have one more. Are you ready for it? One more. 1 minus tangent squared over 1 plus tangent squared plus 1 equals 2 cosine squared of theta. That's it. Okay, we can change the bottom, right? 1 plus tangent squared is secant squared. So admittedly, the left-hand side is more complicated, right? Okay, again, that doesn't mean we have to start there, but it's a pretty good place to start because it looks more complicated to start with. So we can manipulate this now to say 1 minus tangent squared of theta over secant squared of theta plus 1. All right, what might we do next? We've got a couple options, so.
Convert tangent to cosine and sine.
We could convert tangent to cosine and sine. It might not be the next step to do right away. And the reason is because then we're going to end up with those complex fractions we were talking about, and that might not be very friendly looking. So we'll keep that in the back of our mind. And last case resort is always to turn things into sines and cosines. And we could do that. Any other thoughts we might be able to handle?
Would you want to change the 1 to sine squared plus cosine squared?
You might be able to do that, but then I still don't have anything that's simplifying with the tangent. So it's not that it couldn't be done. I don't think it's going to end up being helpful because it doesn't combine with the other piece right away. Yeah?
You distribute that one? It says 1.
Okay, what do you mean by distribute the 1? Okay, that's all right. Well, we haven't seen one quite like this to show this step, so I'd like to mention it now. Do you see that there's 2 pieces of like a fractional piece and a whole number piece on one side, and there's just 1 piece on the other side? So it might be a good idea somewhere along the way for us to combine that into a single fraction. And I think this might be a good time to do that, if we can kind of merge those together. Okay? So I would need to get a common denominator for that to happen. And the common denominator needs to be the denominator that's already there. So this 1 would be secant squared of theta over secant squared of theta. And I still have the 1 minus tangent squared of theta over secant squared of theta. And again, my motivation for thinking that that would be helpful is that when I look at where I'm going, I don't have two pieces added. It's all one singular piece. So maybe combining them will allow some things to cancel out. Now, immediately from the very first get-go, it doesn't quite look like it does, but it actually does. So I want you to take a look back at places where you see tangent and secant and ways to combine them in those identities. Okay, the denominator's cool. We don't need to deal with the denominator right away. It's the numerator that needs some sort of consolation, right? We need to consolidate it in some way. Okay, so I'm going to jot that down here at the bottom. I did this before. Tangent squared of theta plus 1 is equal to secant squared of theta. How could I use, and this is a good identity to use, by the way. It relates tangent and secant together, and it relates the fact that they're squared, and we have things squared on top. So this is a really good place for us to land. Apparently this is our favorite identity of the day. I don't know how I managed to get so many of them that have this identity in them. You will remember this one. You're welcome. You can remember one of them. How could I use this in the top to clean that up? And there's more than one way. So what do you want to replace, Braden?
Replace the secant squared.
Okay, cool. That's what I thought you were going to do. I just want to make sure I was hearing you right. So Braden's idea, and again, there's more than one way to do this, is to say, okay, look, I've got an equation that says secant squared of theta is equal to something specifically. So I'm just going to replace the secant squared part with the thing it's equal to. So the piece at the beginning, 1 minus tangent of squared of theta, will stay. I need to make this a little bit smaller so it's not running into things. There we go. That part will stay. And the part that I circled in yellow will be replaced with what it's equal to down here on the bottom, tangent squared of theta plus 1. All right, so what do you notice then? Careful. The ones don't. The tangents do, though. Yeah. Yeah, so it's really, you're going to be careful about signs, right? The tangent squareds cancel because one of them is negative and one of them is positive. So those add to 0. And my ones don't cancel, which is really good because then I wouldn't actually get to what's on the right. But they do combine. So what do I have in my numerator now?
2.
Yeah, I have 2 in my numerator. So this is now 2 over secant squared of theta. Now, we're still not quite where we were supposed to be, but yes, do you have a question?
Yeah, so we've just done secant squared of theta minus tangent squared of theta.
Yes. Yes, you could have done it that way too. That is there's more than one option. Yeah, you absolutely could have. Did you guys hear her question? Okay. She asked, could we have done, I'm going to see if I can write what you said, tangent squared of theta minus secant squared of theta, you said is equal to 1? Yeah. Is equal to 1. So if you manipulate this equation, you're close. I think you've got your signs backwards over there. But yeah, so if we manipulate this, I promise we're almost finished. Bear with me for a second. We could use this identity and see that I've got a tangent squared and a secant squared and manipulate with that too. That would be another option that we could potentially use. Okay, cool. Let's finish this up. How do I get 2 over secant squared of theta to actually land where I need it to be? Reciprocal identity. The secant is a reciprocal of cosine, which means secant in the bottom is the same as cosine on top. So I can change this. This is 2 cosine of theta squared, and that is exactly where I wanted us to land. We will stop there for today.